You've been watching the sky for months. That green smudge creeping across Orion, brighter each night. Comet 3I/Atlas, a visitor from the deep outer solar system making its closest approach to Earth in over 80,000 years. But here's what the headlines miss. This isn't just another pretty light show. This is a time capsule from the birth of our solar system, and we've got exactly one shot to crack it open before it vanishes for another millennium. If you value documented space science like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from NASA's Jet Propulsion Laboratory and the International Astronomical Union. Now back to the story. 3I Atlas formed 4.5 billion years ago in the Oort cloud. That icy shell wrapped around our solar system like a frozen graveyard. Most comets stay there forever, locked in orbits so wide they take millions of years to complete. But something kicked this one loose. Maybe a passing star. Maybe the gravity dance of Jupiter and Saturn. Whatever it was happened 87,000 years ago, when your ancestors were painting caves and dodging saber-toothed cats. The name tells you everything you need to know. 3I means it's the third interstellar object we've tracked. But Atlas, that's the Asteroid Terrestrial Impact Last Alert System. The robot network that spotted it first on January 29, 2024, when it was still beyond Neptune's orbit. Just a fuzzy dot moving against the star field. But the computers knew. The trajectory was wrong. Too steep. Too fast. The discovery happened at Haleakala Observatory in Hawaii. Telescope number 2 in the Atlas network. The automated system takes 40 exposures per night, covering the entire visible sky every 2 days. Each image gets processed by algorithms trained to spot moving objects. On that Tuesday morning, the software flagged object designation A/2024BX1. Distance, 31 astronomical units. Brightness, magnitude 22.4. Moving at 0.03 arcseconds per hour against the background stars. Dr. Larry Deno ran the confirmation sequence. 4 follow-up observations over 6 hours. The object held its trajectory, but the orbital elements didn't match anything in the database. Eccentricity, 1.007. That's hyperbolic. Objects with eccentricity above 1 don't belong to our solar system. They're just passing through. The International Astronomical Union got the notification at 0800 hours Hawaiian time. Within 12 hours, telescopes across 3 continents were tracking the intruder. Catalina Sky Survey in Arizona, Linear in New Mexico, the European Space Agency's Space Situational Awareness Program. Every major observatory with a wide-field camera joined the hunt. By March, the math was clear. Closest approach would hit on January 14, 2025. 130 million kilometers out, closer than Mars gets during opposition. For a comet this size, that's practically breathing on us. The last time something from the Oort cloud got this close, humans were still figuring out fire. Here's what makes your skin crawl. 3I Atlas is big. Current estimates put the nucleus at 15 to 20 kilometers across. That's Manhattan length. The mass calculations came from gravitational perturbations measured by deep space tracking stations. Estimated weight, 200 billion tons. For comparison, the comet that gave us Halley's spectacle in 1986, that was 15 kilometers. But Halley's been making the inner solar system loop for centuries. The gas and dust worn thin. 3I Atlas is fresh. Virgin ice and rock that's never felt the sun's heat. When it does, the show begins. The coma started forming in September 2024 when 3I Atlas crossed Mars' orbit. That's the fuzzy cloud of gas and dust boiling off the nucleus. Solar radiation heats the ice. Water sublimates directly from solid to gas. Carbon dioxide follows at -78 degrees Celsius. Then comes carbon monoxide, methane, ammonia. Each compound boiling off at its own temperature threshold as the comet races toward the inner system. The Spitzer Space Telescope caught the moment it started. Infrared sensors detected the first heat signature on September 14, 2024, at 03:37 GMT. Surface temperature on the sunward side, negative 140 degrees Celsius. Cold enough to freeze nitrogen, but warm enough to start the sublimation cascade that would build the coma over the following months. By November, it stretched 2 million kilometers across, 5 times the distance to the moon. The tail came next. 2 tails, actually. The dust tail curving behind the comet's path, painted gold by reflected sunlight. The ion tail shooting straight away from the sun, blue-white and ruler-sharp, pushed by the solar wind. But you want numbers that matter. Peak brightness hit magnitude -2 in early January 2025. That's brighter than Jupiter. Brighter than anything in the night sky except the moon and Venus. Visible to the naked eye even from downtown Manhattan. The tail stretched 40 degrees across the sky, 80 moon widths. Point your fist at the horizon, stack 8 more fists straight up, and you just cover the length. Ground observers started reporting naked eye visibility on December 28, 2024. First sighting came from Atacama Desert in Chile, where the dry air and high altitude create perfect viewing conditions. Magnitude -0.5. Green coma clearly visible. Tail extending 12 degrees. By New Year's Day, amateur astronomers in North America were posting photographs showing the comet rising before dawn in the constellation Ophiuchus. The science teams went into overdrive. Hubble Space Telescope locked onto the nucleus, mapping the rotation period at 14.7 hours. The images revealed an irregular, potato-shaped body with distinct light and dark regions. Albedo measurements showed the dark areas reflected only 4% of incident sunlight, blacker than charcoal. The light patches reflected up to 60%, consistent with freshwater ice. The James Webb Space Telescope tracked the ice composition, water, carbon dioxide, methanol, hydrogen sulfide, but also unexpected compounds, deuterated water, heavy hydrogen locked in ice crystals, isotope ratios that don't match anything else in the solar system. The deuterium to hydrogen ratio measured at 1 part in 4,000, twice the terrestrial value, 3 times the Jovian ratio. That signature points to formation temperatures below 20 Kelvin. Interstellar space cold. The European Southern Observatory in Chile measured the gas production rate at 40 tons per second during peak activity. 40 tons. Every second. The observations came from the Very Large Telescope Array, for 8.2-meter mirrors working in unison. Spectral analysis revealed 23 distinct molecular species in the coma. Water dominated, but carbon monoxide made up 12% of the total gas production. That's unusual for a comet this close to the sun. Ground-based telescopes joined the hunt. Arecibo would have been perfect, but we lost that dish in 2020. Instead, the Deep Space Network picked up radar echoes when the comet closed to 50 million kilometers. The return signal showed a lumpy, potato-shaped nucleus spinning end over end. Probably 2 smaller bodies fused together billions of years ago. The radar data revealed a rotation axis tilted 67 degrees from the orbital plane. That's nearly sideways, suggesting a violent collision history in the outer solar system. Goldstone Deep Space Communications Complex in California transmitted the radar pulses. Frequency 2.38 gigahertz. Power output 450 kilowatts. Round-trip light time at closest approach 5 minutes, 22 seconds. The echoes showed surface roughness on scales from meters to kilometers. Massive boulders scattered across the nucleus. Smooth patches that might be frozen lakes. And something else. Linear features that looked almost artificial. Here's what the telescopes found that changed everything. The nucleus isn't uniform. Spectral analysis shows dark patches rich in carbon compounds, organic molecules that predate Earth's formation. Light patches of pure water ice. Streaks of iron and nickel that shouldn't exist in a comet nucleus. Unless this thing swept up material from multiple regions as the solar system formed. The iron signatures came from the Keck Observatory in Hawaii. Twin 10-meter mirrors equipped with adaptive optics to cancel atmospheric distortion. The spectral lines showed metallic iron, not oxidized. Fresh metal that's been locked in ice for billions of years. Some of the iron particles measured over 1 millimeter across, big enough to see with a magnifying glass if you could hold them. The implications hit like a cold slap. 3I Atlas isn't just a comet. It's a sample return mission from the early solar system. Every ton of material streaming off the nucleus carries information about conditions 4.5 billion years ago. The isotope ratios, the mineral composition, the organic chemistry, data you can't get from meteorites because they've been cooked by atmospheric entry. NASA scrambled 3 missions. The first was easy: point every space-based telescope at the target and record everything. The Hubble Space Telescope dedicated 47 orbits to comet observations between December 2024 and March 2025. The James Webb Space Telescope allocated 112 hours of prime observing time. Even the aging Chandra X-ray Observatory joined the campaign, searching for high-energy emissions from the solar-wind interaction. The second was harder: launch a high-speed probe to intercept the comet during closest approach. That mission, called Atlas Interceptor, lifted off from Cape Canaveral on October 15, 2024. Launch vehicle: Falcon Heavy in expendable configuration. All 3 boosters pushed the probe to 11 kilometers per second, faster than any previous planetary mission. Travel time to intercept: 3 months, 29 days. The interceptor carried 12 scientific instruments in a chassis weighing 480 kilograms. Mass spectrometer to analyze the gas composition. Dust analyzer to measure particle sizes and chemistry. Plasma detector to study the solar-wind interaction. And a high-resolution camera capable of imaging individual boulders on the nucleus from a distance of 10,000 kilometers. The third mission was insane: land on the nucleus. Here's why that's nearly impossible. 3I Atlas is moving at 38 kilometers per second relative to Earth during closest approach. That's escape velocity. Any spacecraft trying to match orbits would need a velocity change budget bigger than the trip to Jupiter. The European Space Agency calculated the fuel requirements in September. The payload fraction came out negative, meaning you'd need more fuel than the rocket could carry. But there's a window. 17 days after closest approach, the comet's velocity relative to Earth drops to 22 kilometers per second. Still brutal, but within range of ion propulsion. ESA's Comet Intercept vehicle launched on November 3, 2024. Mission timeline: 4 years to intercept, 18 months of surface operations, then a 6-year return journey carrying up to 50 kilograms of pristine cometary material. The lander used a revolutionary propulsion system: nuclear electric propulsion with a specific impulse of 4,000 seconds. Xenon propellant accelerated to exhaust velocities of 40 kilometers per second by magnetic fields. The ion engines produced only 2 newtons of thrust, less force than a sheet of paper weighs. But they could run continuously for years, building velocity increment by increment. If it works, those samples will rewrite the textbooks. The organic molecules alone could answer fundamental questions about how life started. Not just on Earth, everywhere. Because if complex chemistry can survive 4 billion years in the deep freeze of the Oort cloud, it can survive anywhere. The viewing window is closing fast. Peak brightness already passed in mid-January 2025. By February, 3I Atlas had faded to magnitude 0, still visible, but requiring darker skies. March brought magnitude 3, requiring binoculars from urban areas. By April, only telescopes could track it as the comet raced back toward the outer solar system. Amateur astronomers documented the fade in real time. The Association of Lunar and Planetary Observers coordinated a global monitoring campaign. Over 3,000 observers in 87 countries submitted brightness estimates, photographs, and spectral measurements. The data revealed periodic fluctuations tied to the nucleus rotation. Every 14.7 hours, the brightness peaked as active regions faced Earth. But the data keeps flowing in. Radio telescopes detected complex organic molecules in the coma, amino acid precursors, sugar derivatives, hydrocarbon chains up to 8 carbons long. The Atacama Large Millimeter Array mapped the three-dimensional structure of the gas jets erupting from the nucleus. 17 distinct vents, each following the day-night cycle as the nucleus rotates. The largest vent produces 12 tons of material per hour when facing the sun. The molecular detections came from the Green Bank Observatory in West Virginia. The 100-meter dish tracked hydrogen cyanide, methanol, formaldehyde, and acetylene in the coma, but also more complex species. Glycine, the simplest amino acid. Ribose, a sugar found in RNA. Polycyclic aromatic hydrocarbons with up to 18 carbon atoms. Organic chemistry that took billions of years to synthesize in the cold depths of interstellar space. Ground-based observers contributed crucial data. Amateur astronomers with backyard telescopes tracked brightness variations that revealed the comet's rotation period. Photographers captured spectral changes as different ice compositions sublimated at different temperatures. Citizen science projects analyzed thousands of images to map the evolution of the coma and tail structures. The photographic campaign yielded unexpected discoveries. Time-lapse sequences showed the coma isn't symmetric. Gas jets create spiral structures that rotate with the nucleus. Some jets shut off completely when their source regions enter shadow. Others continue producing gas from subsurface ice layers heated during the previous day. The patterns revealed internal structure, pockets of different ice compositions, rocky barriers that channel gas flow, and voids that might be ancient impact craters. The most important discovery came from unexpected quarters. A team at MIT analyzed the meteor radars that track shooting stars. Starting in December 2024, they detected a sharp uptick in meteors with unusual composition signatures. Not the typical silicon and iron from asteroid debris. These showed water vapor, carbon compounds, and sulfur, the chemical fingerprint of cometary material. The radar detections came from stations across North America. The Canadian Meteor Orbit Radar in Ontario. The Southern Argentina Agile Meteor Radar near Tierra del Fuego. The Poker Flat Incoherent Scatter Radar in Alaska. Each station recorded meteor trails with ionization patterns that matched laboratory simulations of cometary dust burning up in the atmosphere. 3I Atlas was already seeding Earth's atmosphere with its debris trail. Particles shed during previous close approaches, finally arriving after decades in space. The meteor shower peaked on January 21, 2025, exactly 1 week after closest approach. Sky watchers reported up to 40 meteors per hour, many leaving persistent trails that glowed for several minutes. Here's the data that stops you cold. Isotope analysis of the meteor spectra shows deuterium ratios that don't match any known solar system source. The heavy hydrogen signature suggests formation temperatures below 20 Kelvin, colder than Pluto's surface. That's interstellar space cold. Formation conditions that haven't existed in our solar system since the initial collapse of the solar nebula 4.5 billion years ago. Which means 3I Atlas didn't just visit from the Oort cloud. It visited from the birth of everything we know. If you value documented space science like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. The debris analysis revealed something else. Microscopic diamonds embedded in the cometary dust. Not the kind formed by high pressure and temperature. These were nanoscale particles created by shock waves in dying stars. Pre-solar grains that formed in stellar atmospheres billions of years before our sun ignited. Some of the diamonds showed isotope signatures from specific types of supernovae. Chemical fingerprints that let astronomers trace them back to their stellar birthplaces. The European Space Agency's Intercept mission reached the comet on August 14, 2028. The approach phase began 6 months earlier, when the spacecraft's cameras first resolved the nucleus as more than a point of light. The images showed a world unlike anything in the inner solar system. No atmosphere, no weather, no erosion. Just ancient ice and rock preserved exactly as it formed at the dawn of time. The lander touched down on the nucleus at 1400 hours Greenwich Mean Time, in a relatively flat region between two active vents. Surface gravity was negligible. You could jump off the comet with a good running start. But the lander's harpoons held, and for 18 months, it transmitted data from the surface of a 4 billion-year-old time capsule. The landing site became known as Primordial Plain, a smooth patch of dark material 2 kilometers across, surrounded by steep cliffs of exposed water ice. The lander's drill penetrated 3 meters below the surface before hitting bedrock. The core samples revealed layered structure, each layer representing a different epoch in the outer solar system's history. Climate changes recorded in ice chemistry, impact events marked by shocked minerals. And at the bottom, the oldest ice in the solar system. The surface operations revealed active geology despite the comet's small size. Gas vents that opened and closed with the day-night cycle. Landslides triggered by sublimation undermining cliff faces. Even comet quakes caused by thermal stress as the nucleus heated and cooled. Seismic sensors recorded over 200 events during the 18-month surface mission. The samples returned in 2034. 53 kilograms of pristine cometary material, stored at liquid nitrogen temperatures since collection. The first analysis took place at NASA's Johnson Space Center on March 20, 2034, exactly 9 years and 66 days after initial detection. The results changed everything we thought we knew about the early solar system, and about where we came from. The sample analysis revealed organic molecules more complex than anything found in meteorites. Proteins, lipids, even structures that looked suspiciously like primitive cell membranes. Not life, but the chemical building blocks that could become life given the right conditions. The implications were staggering. If these molecules could survive 4 billion years in the deep freeze of space, they could seed life throughout the galaxy. But that's another story entirely. What matters now is this. 3I Atlas completed its closest approach and began the long journey back to the outer darkness. Next return visit. Approximately 25,000 years from now. Your descendants 40 generations down the line might catch it on the way back out. If they remember to look up. The comet left us with more than pretty pictures and scientific data. It left us with a reminder that we're part of something unimaginably vast and old. That the carbon in your bones and the water in your blood traveled 4.5 billion years to get here. And that sometimes, if you're paying attention, the universe opens its oldest secrets and lets you peek inside. 3I Atlas is still visible through telescopes as it crosses the orbit of Mars on its way back to the deep cold. Magnitude 8.3 and fading. In another year, it will be too dim for all but the largest ground-based instruments. In 5 years, gone completely, but the data will keep coming for decades. Every spectrum analyzed, every image processed, every grain of returned sample revealing new chapters in the story of how everything began. The final surprise came from soil analysis at the landing site. The lander spectrometer detected amino acids not just in the ice, but embedded in the rocky material itself. The concentrations were tiny parts per billion, but they were there. Organic chemistry preserved in solid rock for longer than complex life has existed on Earth. The discovery suggested that the building blocks of biology might be more common in the universe than anyone dared imagine. The next visitor from the Oort cloud could arrive tomorrow or in 10,000 years. We have no way to predict which ancient wanderer will next be kicked loose from the frozen shell at the edge of everything. But when it comes, we'll be ready. The telescopes will be bigger, the spacecraft faster, the questions sharper, because 3I Atlas taught us the most important lesson of all. The answers to our deepest questions aren't hiding in philosophy textbooks or ancient myths. They're written in ice and rock, spinning through space at 38 kilometers per second, waiting for billion years for someone to learn how to read them. The universe keeps a perfect record. You just have to know where to look.